Hi everyone, this video is about channels. Up to this point in our course, we've been chiefly talking about efficient, uniquely decodable codes. So we've learned how to produce such things for coding individual alphabets and in blocks. So now we're going to transition to another issue in coding, and that's the issue of reliability. So once we have chosen a code, and we have a message that we would like to code, we might want to take that coded message and send it somewhere. Now, in the process of sending this message, there might be some errors that are incurred, and we'd like to be able to both detect and correct errors occurring in this transmission. So that's more or less going to be the subject of the next few chapters. So schematically, it's a little something like this, right? We have our message, our natural message, M, on some natural alphabet. And then we smartly choose a code, C, to encode this message. Maybe it's Shannon-Fano rule, or maybe it's Huffman code, or something like that. So we now have our coded message. Now we want to send it to someone. And that sending mechanism is what we're going to call a channel. So this coded message gets stuck into this black box channel thing, and then on the other side, something comes out. Now that thing that comes out, this Z that comes out, may not be C of M. It may be something different where there are some errors that were incurred in transmission. Now, once we have Z, we need to use some sort of decision process to decode the message and come up with a natural message, V. And at the end of the day, it would be really nice if M and V agreed with each other. Evidently, channels are important for understanding the transmission of messages. So again, informally, a channel is a means of transmitting messages from a sender who sends inputs to a receiver who gets outputs from the channel. And we want to consider what happens when a source, for instance, is sent through a channel with the possibility that transmission errors may occur. So we're going to let I and J be input and output alphabets respectively for a channel. So that means that I, capital I, is the collection of things that we put in, and J is the collection of things that we can get out of this channel. Now, corresponding to a channel, we have this thing called a channel matrix, which we denote by capital gamma. And remember, a matrix has rows and columns, and it has entries. So the rows of gamma are going to be indexed by our input alphabet I, and the columns will be indexed by our output alphabet J. Now, if little I is in capital I and little j is in capital J, then gamma sub ij is the entry in the little ith row and little jth column. And we're going to want to know what that entry is. So what it's going to be is it's going to be this conditional probability that you see here. So this is the probability that output J is received given that the input I is put into the channel. So this is the probability of output J given input I. Okay. So for example, down here, if our input alphabet I is just the numbers 0 through M, and output J alphabet is 0 through N, then our channel matrix gamma would look something like this. Now let's remember what the entries of gamma mean. For instance, if we look at, say, this entry, right? Remember, that is the probability that output N is received given input equaling 1. So that's the probability of output n given input 1. Here we make a few observations about channel matrices. Here at the top, I'm just reminding you about the definition of the channel matrix. The entry in the I, jth position of the channel matrix is the probability, again, that output j is received when input I is put into the channel. First, this matrix is often called the channel. Even though it's not really the channel, it's often called the channel. Also, it's often true that I and J are identical alphabets. And even more often, it's true that I and J are the alphabet 0 and 1. In this case, the channel is called a binary channel. And we'll be talking more a little bit later about binary channels. Now, importantly, a channel is said to be noisy if, first of all, the input and output alphabets are the same, and if there's an element gamma sub ij that's non-zero for some I and j that are unequal. Now, you can interpret this as meaning that there's a non-zero probability of transmission errors. So why is that the case? Well, if you go up here again to our definition of the ijth entry of the channel matrix, let's suppose now that I and j are different. Then this probability here is the probability, again, that you receive j when the original input was I. And that's what you don't want to have happen, right? You want to, when you put in I, it would be great if all the time you received I back out again. But if instead there's a non-zero probability that you get j back out from this input I, where j is not equal to I, then there's a transmission error. So noisy channels sort of correspond to non-zero probability of transmission error. Okay, and then finally, we're observing that the rows of a channel matrix add to 1. So let's see if we can verify that here. So if we take the sum of the ith row of this of a channel matrix, what is that? Well, that's gamma sub I comma 1 plus gamma sub I comma 2, and so on and so forth until we exhaust our output alphabet, gamma sub I comma n. And then what is that in terms of probabilities? Well, if we just go back up again to our definition of the entries of the channel matrix, this is the probability that output 1 is received when we put input I into the channel. And again, this is the probability that 2 is received from input I up through the probability that n is received given input I. Okay, now in terms of probabilities, what is this saying? Well, the event of getting a 1, the event of getting a 2, etc., these are mutually exclusive events. And so this sum of probabilities that we have here is the same as the probability of getting a 1 or a 2 or an n given input I. But remember that if we put in input I, we must get something from j out, right? And here we've exhausted all of the elements from our output element j. And the probability that we get something out is equal to 1. So this probability is equal to 1. Here we're going to create our very own channel matrix. So we have faces 0, 1, and 2 that are lined up in numerical order at a pie throwing event. So people aiming at 0 and at 2 hit their target with probability 0.9 and hit face number 1 with probability 0.1. People aiming at 1 hit their target with probability 0.8 and hit the other two faces, 0 and 2, with probability 0.1 each. So we're going to write a channel matrix for this scenario where the alphabets I and J are both 0, 1, and 2. Now I is the input alphabet, and we're going to regard I as being consisting of the faces that people are aiming at. So this is our aiming alphabet. J is going to be the alphabet of the outputs, which are going to be the faces that are actually hit. Okay, so here are gamma. That's our channel matrix. And it's we have I and J are both of size 3, and so our channel matrix will be a 3 by 3 matrix. Okay, now that we have our generic channel matrix written down, we want to take these entries and replace them with actual numbers. So in the upper left, if we want to compute, say, gamma of 0, 0, remember that is the probability that people who aim at face 0 hit face 0. And we're told up here that people aiming at 0 hit their target with probability 0.9. So people aiming at 0 hit 0 with probability 0.9. Now we go to gamma sub 0, 1. This is the probability that people aiming at face 0 hit face 1 instead. So people aiming at 0 hit 1 with probability 0.1. And now finally over here, gamma 0, 2, that's the probability that people aiming at face 0 actually hit face 2. So apparently people aiming at 0 can either hit their target or they're going to hit 1. There's no mention of 2. And so apparently the probability of hitting 2 is 0 if you're aiming at face 0. So now we go to the second row. So we want to consider the idea where we're aiming at face 1 and we hit face 0. So people aiming at 1 hit their target with probability 0.8 and hit 0 and 2 with probability 0.1 each. So we have a 0.1 there. People aiming at 1 hit 1 with probability 0.8. And people aiming at 1 hit 2, again with probability 0.1. So now you might want to take a moment and see if you can fill in the bottom row on your own. Okay, well maybe you have attempted to fill in the bottom row. So the bottom left entry, gamma 2, 0, that's the probability that when one aims at face 2, you hit face 0. And that probability is 0. Probability of aiming at 2 and hitting 1 is 0.1. And finally, if you aim at 2, the probability of hitting your target, that is hitting 2, is 0.9. Okay, so that rounds out our channel matrix. And remember that the rows of a channel matrix should add to 1. So that's a good check on your work, is to make sure that each row of the channel matrix adds to 1. Now the question is also, is this channel noisy? So are there any entries in the channel matrix off the main diagonal that are non-zero, and indeed there are, like here and here and here and here. So this is indeed a noisy channel. Earlier we alluded to binary channels. Here we discussed them in a little more depth. So remember, a binary channel happens when both the input and output alphabets are simply 0 and 1. So there are two types now of binary channels. One is called a binary symmetric channel, which has this form. Now, if you remember a little bit from linear algebra, it sort of makes sense that this is called a symmetric channel because the matrix is a symmetric matrix, meaning that gamma and its transpose are identical. Now, this E is called the bit error probability. And you can interpret it as the probability that input 0 flops and becomes an output of 1. And it's also the probability that input 1 sort of flips and becomes output 0. So both gamma 0, 1 and gamma 1, 0 are equal to E. Now, binary asymmetric channel is similar, except that there's not a common bit error probability. This A is the probability that output 1 is achieved when the input is 0. So that's the probability that an input 0 flips to an output 1, whereas B is the probability that input 1 flips to output 0. Those could potentially be different in this situation. Here we see what happens when one passes through two binary symmetric codes in succession. So suppose we've got a couple of binary symmetric codes, gamma and gamma prime, with bit error probabilities E and E prime respectively. So we're going to let G be the binary channel obtained by sending inputs first through gamma and then through gamma prime. Right, so this should be a gamma prime, not a gamma tilde. So we're going to describe this resulting binary channel. So let's suppose we have input I. So there's our input. Remember, I is either 0 or 1. How can we get to output K from input I? Well, first we feed I through gamma, and then we feed the result through gamma prime. So if we take I and we feed it through gamma, there are two possibilities. The output could be 0 or it could be 1. Now the probability that the output is 0 is just gamma sub I0. And the probability that the output is 1 is gamma sub I1. Now, we take 0 and 1 and feed them into gamma prime. So the probability that input 1 is sent to output K under gamma prime would be gamma prime 1K. And the probability that 0 is sent to K under gamma prime would be gamma prime 0K. So now G sub I comma K, so this is the entry in the channel matrix for G in row I and column K. What is that? Well, that is the probability that output K is achieved given input I. And how do we calculate that? Well, the probability of getting from I to k across the top of this figure is going to be gamma I 0 times gamma prime 0k, right? The probability of I going to 0 and 0 going to k, we multiply the probabilities. And then the probability, add to that the probability of the bottom loop, which would be gamma I1 times gamma prime 1k. Now, if you look at this sum, this is the dot product of the ith row of gamma with the kth column of gamma prime. And so that is the matrix product, gamma times gamma prime. That is the I, kth entry in there, right? And so if you want the channel matrix for G, it's obtained by multiplying gamma times gamma prime. Okay, now what would that look like? I mean, if we wanted to write down the entries of this, well, remember gamma has bit probability E, and so this is 1 minus E here. So this is 1 minus E, and then 1 minus E, so that's gamma. And then gamma prime is 1 minus E prime. E prime, 1 minus E prime. And if we multiply those together using matrix multiplication, we wind up with another 2 by 2 matrix. And it turns out to be 1 minus epsilon, 1 minus epsilon, where this epsilon, and you can check this, is E plus E prime minus 2 times E prime. So I guess the upshot of all of this is that this composition of binary symmetric codes is again a binary symmetric code where we can compute the bit error probability for this new code in terms of the bit error probabilities of the previous codes. Now we consider the idea of sending a source through a channel. So we're going to let I, P be a source where our input alphabet I is 1 through M, and P is a probability distribution corresponding to I. So remember, you can think of P1 as the probability that 1 occurs in a string of symbols from I. P2 is the probability that 2 occurs, and so on and so forth. So let's suppose we have a symbol stream from this source, and we want to feed that through a channel, gamma with output alphabet J, consisting of the symbols 1 through N. So that's going to give us a new source, J, Q, where Q sub J is the probability that little j occurs in any given location in an output stream. So it would be nice for us to know, if we know the channel and we know the input source I, P, what is the probability distribution Q for the output source? And this theorem tells us exactly how to compute Q. So if we want Q, all we need to do is take P times gamma. All right, so let's see why that should be the case. So we're going to start by letting T sub ij be equal to the probability that input I occurs in a stream, in an input stream. That's the probability that I occurs, and that the output from that when we employ the channel is J. So we're going to let T sub ij be equal to this. And let's note that T sub ij, so if you want the probability of event A and event B, you need to take the probability of event A, in this case it's the probability of I, times the probability of event B given event A. Now, in the case that the events are independent, it's just the probability of A times the probability of B, but we don't know that we have independence here. So we must use this multiplicative probability formula involving the conditional probability. Now, what is this? Well, the probability that I occurs is just little p sub I, and the probability that J occurs, output J occurs given input I, that is the ijth entry in our channel matrix. So now Q sub J, remember that's the probability that output symbol little j occurs. So we can write that as the probability of J and I equals 1 or I equals 2 or I equals M. And that's the sum of these probabilities. Right, the I equaling 1, I equaling 2, etc., those are mutually exclusive events. And so when we compute a probability involving OR with exclusive events like that, we can just add up the individual probabilities. So that's the probability of J and I, and we add that up for I equals 1 to M, I guess it is. But we know what that probability is, right? The probability of J and I, that's the same as the probability of I and J, which is this Tij. But we saw over here that Tij is equal to this thing right there. And so this is the sum. I equals 1 to M of P sub I times gamma sub ij. And that's that's the jth entry of P times gamma. Right, and that's the end of our proof, right? We wanted to show that the probability distribution Q, that the entries of that are given by the entries of P times gamma. And we did that, right? The jth entry of Q is the jth entry of P times gamma. Here we have a little example where we feed a source through a channel. Our source I comma P has alphabet I just being 0, 1, with probability distribution P given here. And our channel is a binary symmetric channel, gamma. And so that gives us a new source, j comma q, where again, j is this binary alphabet 0, 1. And so the first thing that we want to do is compute what the probability distribution q is. So remember, from the previous theorem, we know that q is p times gamma. So let's see what that is. Well, p is 0.65, 0.35, and then we multiply that by our channel matrix, which is 0.8, 0.2, 0.2, and 0.8. Now, when you do that, how is it that this matrix multiplication is working? Remember that we take 0.65 times 0.8 and then 0.35 times 0.2, and we add those results. And if you do that, you should get something that's about 0.59. And then to get the second entry of Q, we take 0.65 times 0.2, 0.35 times 0.8, add them together, and we get 0.41. Now we check to see whether this makes any sense, right? Remember, Q needs to be a probability distribution, so 0.59 and 0.41 should add up to 1, and indeed they do. So you can think of, in the original source, the probability of a 0 was 0.65 in any kind of stream of symbols, whereas the probability of a 1 was 0.35. Now, once we feed this stream of symbols through our source, the probability of a 0 is now 0.59. The probability of a 1 is 0.41. Okay, let's go on now to item 2 of this, where we're supposed to compare entropies. So first, we have to compute these entropies. So you all should check that this is correct. Right, if you compute the entropy of distribution P base 2, I wind up with something that's about 0.934, whereas the entropy of Q is 0.977. So one thing that we might observe from this is that the entropy of P is smaller than the entropy of Q, which means that sort of the uncertainty associated with probability distribution Q is greater than the uncertainty associated with probability distribution P. And that sort of makes sense, right? We already have some uncertainty in the source I comma P, and then when we feed it through this channel, there are certain, bit flips that could happen that are going to increase our uncertainty. Our intuition that uncertainty should increase when we pass a source through a channel turns out to be accurate in the event that the channel is a binary symmetric channel. So that's the point of this theorem. So if we have gamma, which is a binary symmetric channel with bit error probability E, and a source I comma P, if we feed that source through gamma to obtain a new source, J comma Q, then the entropy of the output distribution is going to be bigger than the entropy, or bigger than or equal than the entropy of the input distribution, which can be interpreted as saying that the uncertainty here is greater than or equal to the uncertainty here. So how do we prove that? Well, here we sketch the proof of this theorem. So we're going to form a function, little h of x, which is the entropy, where the default, it's base 2 entropy of the probability distribution x comma 1 minus x. Now you can use calculus to show that this function, little h of x, is increasing on the interval from 0 to 0.5 and decreasing thereafter, and has a maximum at x equaling 0.5. So this is something we talked about in class near the beginning of the term. Now let's suppose that our probability distribution p, since this is a binary symmetric channel, our source alphabet needs to consist of 0 and 1, and so our probability distribution is going to be just merely a two-part probability distribution, some x naught comma 1 minus x naught. And we may as well assume that x naught is less than 1/2. So let's suppose that the bit error probability E for gamma is also less than 1/2, or less than or equal to 1/2. Then when we take Q, which is P times gamma, we wind up with this probability distribution. And to make the notation a little simpler, we'll just let Y naught be equal to this object right here. So it turns out that this Y naught is bigger than or equal to x naught, and it's less than or equal to 0.5. So that means that if we look at the entropy, the base 2 entropy of Q, that is the same as little h of Y naught. But because Y naught is between x naught and 0.5, I know because h increases on the interval from 0 to 0.5, that h of Y naught is bigger than or equal to h of x naught. But h of x naught is exactly equal to our base 2 entropy of P. And so that proves the theorem. Now, it turns out that this theorem is not true for asymmetric binary channels. You all ought to check this out. Try letting P be the distribution 0.5 comma 0.5. That corresponds to the situation where we have the very highest level of uncertainty in our input source. Now, when you pass that through a binary asymmetric channel, then the output distribution, in fact, will have more certainty than the input distribution.